Okay, hello everyone. So today is our third session about PhD student, postdoc, and other people showing in very very short time the work they are doing. Today we have three PhD students. The first one is Razanne Abu-aisheh from Nokia Bell Labs. The second one is Gabriele Castellano from Inria. And the third one is Camila Fernandez for Nokia Bell Labs. So, Razanne, you can start your talk.
So as I was introduced, my name is Razanne Abu-aisheh, and I'm doing a CIF with Nokia Bell Labs and Inria. And today I'm going to talk to you a bit about my work on Atlas for exploration and mapping with a sparse swarm of networked robots. So problem and context. Now, with multi-robot systems and general autonomous systems, they are expected to be able to execute critical tasks in real time without any human input, and they have to do this in basically a limited amount of time and to do this efficiently. However, the problem with this in what currently exists is that these tasks are mostly complex. They are very time critical and they have to be fully autonomous. And when you have this with a lack of an understanding of the relationship between the robots moving around and their surrounding environments, then this raises a lot of inaccuracies, which could be, for example, a misrepresentation of the data because of a lack of an understanding of their surrounding environment, or a mishandling of an event because of this, and so on. So in general, our work aims to improve the efficiency of autonomous systems mission execution through gathering and processing contextual information from multiple sources, as in like multiple agents or robots, and converting this knowledge and this understanding of the surrounding environment and the context into actionable knowledge, which can help with the execution of the mission. So methodology and related work. Now, in order to collect and gather sensory information in general, robots need to be able to move and roam around. This implies two things. First of all, they need to move around in an efficient and timely manner, and they need to do so while avoiding obstacles and hazards. So this implies exploration and navigation and mapping. And this also implies a certain level of communication between the robots. Now, what we have done is we have compared various existing exploration and mapping algorithms, and we have found that they tend to be either inefficient with a certain number of them, or they rely on a high number of robots. And also most of them do not take context and inaccuracies into account. So we then developed Atlas, which is our own exploration and mapping algorithm. And we did this with our own simplistic simplistic open source simulator, which we developed in order to simulate exploration and mapping algorithms, both with and without inaccuracies. So what we did is we compared, first of all, state-of-the-art algorithms that exist there. And then we compared state-of-the-art with Atlas. And then with Atlas, we worked on it without inaccuracies in terms of communication. And then we started to add communication losses, inaccuracies to compare the performance in both situations. So results and current work. So as you can see here, this is a screenshot of our simulator, just to show you kind of what it looks like. And then here you can see is we have a comparison between Atlas, which is our algorithm, and various state-of-the-art algorithms. And you can see how it, so this is the number of cells it discovers, and this is the time it takes. So you can see that Atlas is outperforms the others in terms of exploration time. But this is all with ideal communications. So here what we do is we take Atlas, and then we try it with ideal communications, and then we add packet losses, and we compare the best case scenario and the closest to the worst case scenario, which is a PDR of 0.1 as a packet delivery rate of 0.1. And we emphasize on the importance of taking inaccuracies into account when designing any algorithms that require coordination between robots due to the huge kind of difference in performance that you can see. And then what we aim to do after in the next steps is to add further inaccuracies, first of all, and then to start to take these inaccuracies and take our understanding of them and utilize this to actually make the algorithm more efficient by understanding these inaccuracies and understanding them in a contextual manner and using that to add and enhance to the efficiency and performance of the algorithm. So that was a 3-minute summary of my work. So if anyone has any questions.
So thank you, Razanne. So for your information, it's a bit less than 5 minutes.
Oh, really? Oh, wow.
Okay. But it's normal. But it's, for me, we will be back after at the end on the comment. The format is, I think, is okay, but you will need to be a bit shorter for the at least for the workshop.
How much did I take in total?
4 minutes, 50 seconds.
Oh, okay. Noted.
No, it's a first try.
Okay.
So, any questions in your audience?
Any questions for me? Or
no, for the people, the attendees.
I have a question.
What kind of robot do you target?
Sorry?
Do you have a particular model of robots that you target to model?
Yes. So what we have is
There are some noise.
Ah.
I think maybe it's okay.
Yeah. So what we are aiming for is to work on swarm robotics, which are simplistic robots with limited capabilities. So we are there's 2 things. So we already have JetBots and TurtleBots at the team at Nokia, and we are also at the team at Inria working on building our own platform of the little minimalistic swarm robots. And then we aim to have once we finish all this work with the simulation, we aim to have like a heterogeneous kind of swarm with the 3 platforms that I mentioned to actually apply these algorithms on in real life.
But when you say that you map, it means that you have some kind of sensor. So
yes, so the map is built by using a bump sensor. So basically what happens is whenever the robots, we assume that they're very small, and then whenever they bump into a wall, they just, so if you want to know more about the actual algorithm, so we have a centralized controller and then we have an actual multi-robot system. And then when the robots bump into a wall, the robot will stop and then it sends a notification to the central orchestrator. And then the orchestrator basically just puts a dot on the map. And then every time you have 2 dots that are kind of a certain distance apart, it connects them into a line. And then when you have lines that are a certain distance apart, they connect into each other. So we end up with an outline of all the obstacles.
okay, thank you.
Daniel,
Hi. I will have a question as well. You mentioned that you are trying to take into account the context information.
Mm-hmm.
Taking account context information for artificial intelligence is one of the more difficult problems that the community is working on today, right? So can you say something more specific about that?
Sure. So for now, the first element of context we're looking into with the exploration and mapping is, for example, connectivity. So we assume that, for example, the quality of communication can be considered context because this can be utilized later on. So if the system understands, for example, the quality of communication across the arena, it can utilize that to improve the actual exploration. So you can send, for example, robots to certain areas based on the quality of the communication, or you can work on placing relay robots in certain areas based on this knowledge. So that's, for example, one contextual aspect. Now, later on, for example, we want to enhance this to go into, for example, a target detection as well. So when you have something like target detection, you can have inaccuracies as if, let's say you have a source of heat, for example, like to say you want to detect a human through infrared and a source of heat. You may have other things that are also emitting heat that can be some sort of like false positive. So you want to be able to distinguish your false positives from your actual sources of heat and so on. So those are the elements that we want to like gradually add on to kind of investigate how we can take that into account with the algorithm.
Yeah, I perfectly understood the, I think, for the first one. For the second one, this is typically these very difficult layer problems for robots, right? That's why I was asking if you have some hints about the methodology that you will use to make some progress on this domain.
Yeah, so as I said, like now what we're looking in mostly is in the communication aspects. Now with the target detection, we're still like in the early works, but what we are looking to have is some sort of it's still very early work. So, but the idea is we want to like first of all collect our own models of like how kind of like infrared could spread with like if you have a human moving around, and then we want to like look into building our own model and trying to do some sort of like maybe machine learning in that area to kind of like spot out anomalies. But again, like I don't have exactly the exact like methodology for that in mind yet. We're more still on the navigation mapping and the communication context of things.
Thank you.
Other questions? I have one. Razanne, can you give some concrete application of what you are doing, concrete scenarios in the industry or elsewhere?
Sure. So for exploration and mapping, like this can be applied to pretty much anything. So let's say, for example, you have search and rescue now, which is an important application in this area. So you have an unknown environment, and then you want to put like a swarm of robots in there, and you want them to, for example, locate victims. So you put them into the area, they have no clue what the environment looks like, and then they have to kind of build a map of the area, and then they have to localize targets so that they can help the kind of actual rescuers move safely to the actual targets. So that's one application. For example, another application is if you want to have, like, for example, patrolling of an area, like you know that you have an intruder, and then you just put these robots, and then you want these robots to kind of like locate and find your intruder, so for security reasons. Also, for example, in a factory, you can say you can have leakages, for example, chemical leakages or something. So you want to be able to localize the source of your leakage at some point. So you put the robots, they have to be able to, first of all, build a map of their area. They have to be able to do this as soon as possible, while also trying to find the source of the leakage. So these are all time-critical missions where you need the exploration, mapping, and target localization to happen in the minimum amount of time possible.
Okay.
Yeah.
Okay, thank you. There are already several examples. Thank you very much. Other questions? So maybe we can go to the next speaker. So Gabriele Castellano.
Yeah, hello. I share the screen. Okay.
So we can see you. It's also with it's within the. I suppose it is within the common lab with Inria.
Yes.
Yes. Okay. No, I saw Inria, but I saw also on your slide the Camila. So, okay. So maybe we can. You can start. No.
Okay. Hello, I'm Gabriele Castellano. So yes, my project is a joint project between Inria and Nokia Labs. I'm actually a postdoc from Inria. And my research is addresses a problem that is arising on resource-constrained devices, where more and more applications requires to execute complex tasks using machine learning models, such as object detection, classification, speech recognition, and so on. So these models can either be run and computed on board of the devices or offloaded to remote clouds. So when we execute them locally, devices can only afford to run light models, providing low accuracy results. While if we offload these models to a remote computation in the cloud, we have an additional latency because of the network that is in between. So there is this trade-off between accuracy and latency. So to address this problem, we model a system that exploits the continuum of resources that exist between the cloud and the edge. So the request to perform this task can be served in one of the nodes that is found in between the source of the request and the cloud, where we for sure we found a suitable model to process the request. So in this network, we can have multiple models that can answer requests for different tasks, and for each task we can have also like a variety of models of different qualities. And every node in the network can have also different resource constraints. So the models that are run on every node can be different. And additionally, also the models can have a given constraint on the number of requests they can process. So at a certain point, one model can be full of requests per second and cannot serve any other streams, for instance. When a request is served on any of this model, we experience a cost that is a trade-off between latency and accuracy. And the fact that there are intermediate models on this path between the edge and the cloud can reduce the serving of this cost, the service cost. We designed an algorithm to maximize the cost reduction, and this algorithm is distributed, so it takes decision based on local information, and we show it provides strong performance guarantees. So in these three graphs, we can see for different settings of the trade-off between accuracy and latency, how the system decides to place models on the network. So we can see that we have different tiers of serving. Number 4 is more at the edge, number 0 is more at the cloud, and this is the average allocation of models. From left to right, we have models with increasing quality. So when we give more importance to the latency, we see that the system prefers to allocate lower quality models at the very edge, and vice versa. We compared our solution against the greedy approach, and we see that it outperforms the greedy. Our solution outperforms the greedy for various setting of the trade-off, and also for increasing the number of requests per second. Thank you.
I was on mute. Okay, thank you. So it is a bit less than 4 minutes. So 3 minutes and 50 seconds.
Okay.
Okay, thank you. Any questions in the audience?
Perhaps one question.
Yeah.
So there were, in a sense, similar problems when in the setting of databases and Akamai type things, where people were trying to have replicas of or subsets of databases close by. Could you elaborate a little bit on that and stress the thinking and these new problems?
Yeah, exactly. So also the name of that I used in these slides, as you see, is inspired from content delivery network. So here we talk about the inference delivery network. The fact is that we know that there is in the cloud we can put whatever we want, so we can allocate models to serve every kind of task, and then like as it happens in content delivery network, if we find something in between, we can serve there instead of going in the cloud. The difference with that is mainly the fact that each of these model that we use for serving the request has a bounded capacity in terms of the number of requests it can serve. So if we allocate a model on this node, for instance, this, we know that all the requests that pass from here, and then because they will want to go, for instance, in a common cloud, they can served by this model, but up to a certain request per second capacity. No? So at a certain point, if there is enough capacity on the node, we can allocate either another model that can have the same quality or a different quality, or the request should be served elsewhere. That can be closer or farther. And closer and farther doesn't mean like less cost and higher cost, because the cost is also a combination between latency and accuracy. So it is not trivial that the farther we go, the less cost we achieve. So this is these are already two differences. And then there is also another difference that is the items that we are allocating on the network that are these inference models. They are not just like an item that can be there or cannot be there. Each task can be served by different qualities levels. So for each task, we can have different items that can, and we should try to understand which one is best to serve a given task in a given moment based on the allocation that there is in the path. So these are like, this is a summary of the differences that we encountered in like trying to get inspired from what happened in content delivery network, but adapting it for the inference use case.
Thank you.
I have a question. Maybe I did not understand well your problem, but if I understand well, you have a problem. You have different nodes able to answer this task with more or less evolved neural networks, for example. And so you route this query through the path, and you stop when you find a node able to serve the query. Is it correct?
Actually, our algorithm decides not only the routing that a request should perform, but also the allocation that each node should decide. Like at every moment, this node have to decide, okay, there is a catalog of tasks, and for each task, there is a catalog of suitable models. In this model, in this moment, it is optimum for me to run this quality of model for this task, or this set of models based on the capacity.
Okay, so it's rather you have a set of tasks, and you try to scatter this set of tasks along the path.
Exactly, yes.
Okay.
So there are many paths, and at last we always assume that in the cloud we run the best model that can process every number of requests and at the best accuracy. But then in between we have to decide, because there is a limited amount of capacity. We have to, every node needs to understand based on limited information from the neighbors and based on the request that arrives, which is the best model to run in a given moment.
Okay, and how do you decide whether a neural network is able to answer this particular subtask?
No, we just assume that this is well known. So every request is labeled with the task name of the request. So for instance, a task can be object detection for a particular training set, no? And then we know that there are, I don't know, 10 models that have different resource requirements and different provide different accuracy, and they are suitable for answering that that request, that family of requests. And so, yes, in a given moment, a node can decide, okay, maybe I'm seeing a lot of requests for this task, and for me, it is better to run this particular quality level for this task because of my resources, because I also running other models in the meantime for other tasks, and so it decides to allocate that.
Okay, last question, if I may. In this case, what is the difference between your problem and a classical NDN or CCN problem? Because as you use label to annotate the task you might need to solve, this corresponds to name in named delivery network or content-centric networks. So I have the feeling that the problem that you are trying to solve in this work is the same than the one that was solved in CCN. Am I correct?
So the difference is, I think, is the same that I answered before. The fact that these models have limited capacity for serving requests. So once there are streams of requests that arrive, they can saturate the models. You cannot say, assume that an allocation of an item, like it happens in those kinds of network, can serve everything below, and you just have to decide which item to allocate in which place. Here you have also to to optimize this trade-off. I mean, when you use resources of a node to allocate an item, then the item can just serve a particular number of requests per second, and so you have to decide which. Also, if you forward a request up to a given node, and then the node has the model but is saturated, then the request should still go up, or maybe the optimal solution for that particular request can be to be served, and by optimal I mean the second optimal, because maybe the optimal was to be served here, could be still to be served in the first hop, because there was another model before, but it's not optimal because the network latency is less, but the accuracy it provides is also less. So maybe according with the setting of the trade-off, it was better to be served in the second node. While in this case, if the second node is already saturated, you need to still to process on the first node, and you have to figure out this before. Otherwise, you are losing this extra latency with no reason. So there is a set of differences with those kind of problems that we find out when modeling this this system.
Okay, thank you.
Other questions? I also have one for this presentation, Gabriele. So for what I understood, you suppose that you have a good knowledge about the models that are deployed in each node, and how much time, how much requests they can each node can serve, and so on. But what makes me a bit afraid by this kind of solution is that you may have many tasks that could be solved in each node with different models. What is how your system is depends on the accuracy of the knowledge you have about what the nodes can do, because it may not be easy to know exactly how each node will spend, how much time each node will spend for each task.
Okay, yes. So we assume that on every node we can switch the models and the tasks. So at a certain point we say, okay, it is better to serve a different task, or maybe to allocate less resources for this task and start also serving another task, and we decide which model to use. But as you say, yes, we assume to have like profiling of the models, how they run on each node, so that we can foresee how much time, like what is the computation time that the task needs on each particular node according to each particular model.
Do you have some examples, concrete examples of some tasks with different models, and how much time it takes for each model?
Oh, yes. So for object detection task, for instance, we in our evaluation we use the YOLO model, that is state of the art on object detection, and in a server equipped with the GPU, we can run a single inference, so the fastest thing you can imagine, with batch size equal to 1 in a little bit less than 30 milliseconds.
Okay, so there some figures exist. I didn't know that. So okay, some figures exist on some tasks, and so you can already have an idea about it. Okay. Okay, thanks. Okay, so maybe we can switch to the last presentation. So Camila. Yeah, stop. Yeah. Gabriele, you need to stop your sharing.
Yes.
I can see your screen.
Gabriele, we still see your screen. Can you stop sharing?
Okay, I found the button.
Okay, Camila.
I don't know where I'm here. So do you see it?
Yeah, you can go to the full screen. It will be better.
Yes,
Yeah.
sure.
Is that okay?
Okay. Okay. So my name is Camila Fernandez, and I'm actually working in doing my PhD with Nokia Bell Labs and Sorbonne University. The name of my project is Time to Event Analysis, and I will show a little bit what I've been doing these last 6 months. So to start, the idea is that we want to predict the time until certain critical event occur. And here I have some examples. So we would want to, for example, predict the customer churn for an enterprise, or if someone who was in prison will come back in prison, or also in health. We can predict if someone will die, or if someone will get a disease again. And predictive maintenance is another very important application of this type of models. And one of the very important things in comparison with classical predictive modeling is that here we have something called sensor data, which means that not all the samples in the data set have reached the critical event. So we will consider, for example, in the customer churn prediction, also clients who has not churned yet. And so the objective of the project is to implement new methods with theoretical guarantees that outperforms the state-of-the-art ones. And so how we implement these methods? So we have a data set, we split it in training and validation, and we feed the model. Then with the features of the validation set, we predict the survival probability function, which is what we are trying to estimate. And then we compare these predictions with the data set to get a score, which will tell us how good was the model. So at the moment, what we have done, so here I have an example of one particular data set of a telecom company. So we, first of all, we compare different types of scores. And also we implement some statistical tools, like to know which features are more important for the predictions. Or also here we can compare, depending on what type of contract a client has, how is the probability for them to churn. And also we have been implementing new methods. Here there is a small graph, so we are working in ensemble methods on different optimization algorithms for choose the best parameters for the aggregation. And so here we can say how there is a little bit of better performance in some combination methods than the methods like only considering one method at one time. And that's a resume of what I'm doing. So thank you.
Thank you, Camila. So 3 minutes, 20 seconds. So
yes.
Good.
Yes.
Okay. Any question in the audience?
Anastasios, hello.
Yeah, Anastasios.
Hello. So I have a question regarding the prediction. As I understand, what you do is that you feed in the model the current state of the system that has to do with a bunch of features, and then you make a prediction of what is the probability to churn.
No, the prediction. So yes, we first we have some features, so we fit a model, and then we can estimate the probability function, and with this function we do a prediction of the time.
So you predict the whole PDF, the whole CDF of the time.
Well, whole, yes.
Yeah, but I mean, this is okay. So I have two questions about it. The first is, have you observed, for example, with your models, if I guess when an event tends to go to churn, then this probability should be increasing, I guess, as we approach the churn, right?
Yes.
So have you seen such type of let's say correlated events as you approach churn, for example?
Yeah, well, actually, okay, so first of all, like we are estimating the opposite probability, like 1 minus the probability to churn. So it's this, we call it the survival probability. So it's at the beginning, it's always 1, and then when the time goes on, the probability to churn is each time higher, so the probability to stay is each time lower.
So this is what I'm asking.
I like this.
Yes. So I'm asking, like, there is you have observed exactly this temporal correlation of events. It's not so the time actually plays a role in your model. The temporal evolution is not that just an instantaneous feature value that gives out the result, but you have some correlation over a time window.
Yes. Yes.
Okay. Okay. And when you say a model, you mean some general model like a deep network or something more specific?
We implemented many. So in this case, we have a Cox, which is I think the most famous one, but also some deep networks. I mean, some models that use deep learning tools, or some other statistical tools. But there are different models. And we are also working in new ones new machine learning models, basically. And this one particularly is a very easy one. So yeah, but there are many, so it's not like one particular model.
Okay, thank you.
Other questions? I have one from my side. So can you come back to the last slide? So I see that you have some results presented here. What was not clear for me, I suppose that what you do is you are simulating. Do you have a model for simulating the things, or do you have some real data?
This one is a real data.
Real data. Okay.
Yeah, I mean.
Maybe you told me. Maybe you told me. I don't remember.
Yeah. It's a Kaggle dataset. It's a telecom company, so the idea is to predict the churn. I also did simulations, by the way, but I didn't put any of that here because
what is interesting is that it is real data. Yeah.
Okay. Yes, and we have 2 other ones from health. Yeah.
Okay. Other questions? So thank you for the 3 of you for your presentation.